what if you would like to explain a variable y, and of course you include the intercept, you include the coefficient on the treatment variable. In this case, the treatment variable is denoted x, but it still is a number between or equal to either 0 or 1. So x is equal to 0 if the person I here did not get the treatment, and equal to 1 if person I got the treatment. But we have a problem, because this x, the assignment of treatment, is not entirely random. And we saw in the previous video that we could add some control variables, w, in order to reduce the omitted variable bias here and make x random conditioned on the control variables. However, sometimes you do not find the control variables, or there might be a lot of control variables, but if you could find a variable which is randomly assigned, for example, a control variable which influences the y variable only through the x variable, but this z, this control variable, is itself not correlated with the error term, then you can use instrumental variable regression. So what we need is that the instrumental variable influences the probability of getting the treatment, and of course you have to have data on both the treatment and the instrument, and z must be random. To shed some light on this, we can consider the following example. It's based on Ankrist 1990, and he wanted to investigate the effect of serving in the military had on earnings. So the military variable is a binary variable, which is 0 if individual I did not participate in the military, and 1 if person I actually went into the military. So what you can imagine here is that you have a lot of omitted variables which might be relevant in explaining the variation in earnings, but they are also correlated with whether or not someone served in the military. So one approach would be to add some control variables here, but in this case you could add a lot of variables, because a lot of variables might be correlated with military participation. So an easy way out is to find a instrumental variable which extracts the randomness out of the probability of serving in the military, and use that random part of military participation and regress that on earnings. Because if you get a random part of the military participation, then on average this military participation variable should not be correlated with any other variable. to extract the random part of the military, you would have to find a random variable which affected the probability of participating in the military. And during the Vietnam War, you would actually have this random variable because they had a lottery system. And this lottery system affected the probability of being drafted into the army or into the military. So there was a national lottery, and the days of the year were randomly ordered, so they are just shuffled up and randomly chosen, and those with birth dates ordered first were drafted before those with birth dates ordered second, and so on. So if you got a low lottery number based on your birth date, you were more likely to serve in the military. So the probability of serving in the military would be higher than for those who got a high lottery number. So the lottery, if we look at earnings, it's a an intercept times the binary treatment variable times the or plus the error term, and we can use the lottery number z as our random part of actually serving in the military. Okay, so this is whether or not, this x is whether or not the individual served in the military, but this is affected by a great number of factors or variables, but this random part is the lottery, and the lottery result can be used, because it's random, as to extract the random part of the x variable, and then we can use the x variable or the fitted values to explain earnings, because in this case we are interested in the beta 1 coefficient, and we would like to get an unbiased estimate of the beta 1 coefficient, because this would give you the difference between earnings of those who participated in the military and those who did not. The question here is whether or not we have found a valid instrument. So we need to satisfy two conditions, and the first condition is relevance. Okay, and this means that the lottery number should affect the probability, should affect the x of serving in the military. So in practice, we can check this by estimating the first stage regression and implementing the hypothesis test that the coefficient on the instrument is 0. So you just apply the regression of x on z. And in this case, the coefficient on the z variable should be different from 0. And the second condition is exogeneity. And this means that the correlation, or equivalently the covariance between the instrument and the population error term, is 0. And this is difficult to test, but it's in our case likely to be okay, because the lottery number in itself was random. And if you take the correlation between a random variable and something else, then the expectation or expected correlation is actually 0. Although we would have a problem if our random variable was inducing a change in behavior of those who were in the lottery, such that, for example, if those with a low lottery number stayed in school longer to avoid being drafted into the military, then you would have this random part in Z, but it would be corrupted by the school years, which would affect the x variable. And so in this case, even though the instrument itself is random, if this random part is not followed directly to the x variable, then you would have a correlation between the supposedly random part in x and, for example, school years.